Students, welcome to New Year. Wishing you and your family a colorful, joyous, happy, healthy and prosperous 2021. Happy New Year to all my dear students and my friends. Welcome to our online classes on continuation of Induction Motors for 5th semester Diploma Electrical students. Today we are going to learn a few interesting topics regarding to the torque produced in induction motor. You can see the induction motor torque under running conditions. As already we have covered how the power input to induction motor converted into mechanical energy in different stages from stator to rotor. As we know that the energy cannot be created, cannot be destroyed. Whatever the electrical energy given to our motor, three-phase induction motor, that is converted into mechanical energy. During this process, it will take a different stages of changing its power, wasting up its power. That means, so there is a input minus output, there is a losses takes place inside the induction motor. What are the different type of the losses? These losses may be in the form of core losses, copper losses and friction and windage losses. Which type of the losses may be occurred at from stator to rotor, we already calculated and we understand with problems. Further, in this class we are going to learn how the rotor will rotate. As we know that once three-phase supply is given to our induction motor, what is happen? You know that synchronous speed is developed, a rotating magnetic field is developed, RMF is developed in stator core, stator field winding, that is running at a synchronous speed. This magnetic field, whatever induced in the stator, is passed through air gap towards rotor. Our rotor also has its rotor windings. Due to this change in magnetic flux of RMF, and it is a 1.5 times of magnetic field, but it is rotating in synchronous speed. The relative speed between this magnetic field RMF and stationary conductors of rotor, it induces an EMF in the rotors as per Faraday's laws of electromagnetic induction. Just like at standstill, we know that our three-phase induction motor similar to three-phase transformer. Now, how this torque is developed? At which the torque is developed with maximum? What is the starting torque? What is the pull-out torque? How the torque is varied from starting to full load? If the load is added further, then automatically motor will stop. Then at that condition, how the torque is changed? What is this performance? So, as electrical students, we should know. So, what is the where is the range of operating range? Where is the critical range? We are going to learn in this session. Okay, let us, before going to our main topic, what are the objectives today, on completion of this period, you would be able to know that one is maximum torque equation, relation among the full load torque, starting torque and maximum torque, and at the same time rotor parameters. Already we last class we have seen some introduction, and how the torque is developed already we have seen directly. So in this class, how these parameters changes in rotor if rotor starts to rotate near to synchronous speed. So that means, so there is slip speed. At that condition, what are the rotor EMF, rotor frequency, rotor reactance values? These factors, how the effect on current and power factor of rotors, and overall how the torque is changes based on this speed at slip speed. Okay. Now at the same time we will compare what is the starting torque and compare the starting torque with the full load torque and maximum torque with full load torque. At the same time we are going to derive the equations at which it reaches the maximum speed. It depends on what factors. Okay. These are the very interesting, dear students. Please listen carefully. Okay. So let us see one by one. As we know that here this 3-phase transformer is similar to our induction motor, 3-phase induction motor. What are the primary is the stator. What is the secondary? That is equal to our rotor. Under standstill condition, that means n is equal 0, rotor speed is equal 0. So whatever the EMF induced in the rotor, that is equal to E2 induced in the rotor is near, that is just like secondary induced EMF in transformer, and frequency of rotor equal to frequency of primary of our as well as the secondary of transformers. Reactance. So anyway, R is equal to independent of frequency. If frequency changes, what will happen? So reactance value changes. What is the reactance of omega L? That is equal to 2 FL. Okay, that means under standstill condition, these all identical. These values are identical. Okay. Last class we have seen all these things. Now we are going to learn clearly with help of this one. Okay. So what is the factor? Just recollect what we have seen last classes. The value of EMF induced in the rotor at standstill is maximum because the relative speed between the rotor and the revolving stator flux is maximum. The RMF is rotating at a synchronous speed. Our rotor is at the standstill speed, that is called 0 speed. So the relative speed between the rotating RMF and rotor conductors is a maximum d phi by dt, that is more EMF induced, just like it acts as a secondary of transformer. In fact, the motor is equivalent to a 3-phase short circuited secondary. Okay, just like secondary is the rotor is a short circuited conditions, whereas in case of the slip ring induction motor also it is shorted with the external resistance. We have seen all things this one. Okay. Now coming to the values. What are the values we have seen? So here, so for this one, so E2, what is the EMF? That is the EMF standstill, rotor induced EMF for phase values, and I2, the rotor standstill current for phase, X2, the standstill rotor reactance for phase, F2, rotor current frequency at standstill condition. Okay. So these are the rotor values. What are the stator values? You know that stator values is equal to, that is the E1 is the EMF induced the stator to the self induced EMF, frequency of supply, I1 is the stator current, and these are the values are where the X1 is the values of stator winding reactance value. Okay. So these are the, that means 1 indicates that stator values and 2 indicates the rotor values at standstill condition. Dear students, 1 for, okay, here 1 for stator values, stator winding values, whereas 2, that means, so E1 EMF of stator, self induced EMF in the stator, and E2 that is equal to EMF, that is equal to EMF induced in the rotor values, rotor winding parameters under n is equal 0. So rotor is standstill condition, no movement, whereas E2 ER, that is at rotation moment at slip speed, rotor EMF induced at speed. What the speed? That is called, we can then, so indicated by the R. So ER, that is equal rotor induced EMF at a speed of S, that is a N, or at a slip speed S. Okay. So here this is the rotor induced EMF, this is also rotor induced EMF, this is the rotor speed is 0 at starting, at rotor speed is at slip speed. Please do not confuse. Okay. So these are the parameters you have to remember. Now at the same time, when the rotor is stationary, S is equal to 1. What is the S? Slip. What is the slip? What is the slip speed? So ns minus n, that is the synchronous speed minus rotor speed. What is the percentage of slip? That is ns minus n by ns into 100 is the percentage of slip. You know that thing. Now S is equal to 1 at that starting condition. The frequency of the rotor EMF is the same as that of the stator supply frequency, just like it acts as a simple transformer. Okay. Now at the same time, we have seen when rotor starts running, the relative speed between the rotor conductors and rotating stator flux is decreased. Okay. So what, do not confuse this, dear students. So what you have seen, once again I am giving this one. Okay. So what is happen? So normal condition have 2 conditions. Case 1 at standstill condition, that is the here the stator and this is the rotor. This is the rotor. Stator is the stator winding, 3-phase winding, distributed winding, 120 degrees apart. Here R phase, Y phase, B phase. We are given the voltage, that is the V1, frequency we are given the F1. It has the values of Z1, impedance values, resistance values, or reactance values. Now rotor, this condition at rotor speed, the speed is locked now. So n is equal to, speed is equal, rotor speed is equal to, here I can write it the 0 at standstill condition. Okay. Now what is the this parameter, similar to this parameters? What are the parameters now? So this parameters is equal to EMF induced is equal to E2, frequency is equal to F2, and its a reactance is equal Z2. Okay, at standstill condition. It acts as secondary of transformer, it acts as a primary of transformer. Case 1. Second case, what is happened? So, here the stator is a common, okay, stator is a common, but our rotor is rotating at a speed of n rpm. Okay, now n is equal to some, for example, you take the 14 or 1300 rpm. Okay, what is the synchronous speed? Here the frequency is equal same and V is equal to V1 F1 and here impedance is equal to Z1. Whereas rotor parameters now changed. What is the ns synchronous speed of this one? Stator field, stator magnetic RMF rotating magnetic field, we can calculate it, that is equal to ns. What is the ns? Ns is equal to 120 F by P. Okay, let us assume for the 4-pole machine. So, ns is equal, we can write it here, ns is equal to 120 F by P. P is equal number of poles, that is we are going to the 1500 rpm. Okay, 1500 rpm we are going to get it. Now, here the speed is the 1300 rpm, so rotating magnetic field is the 1500 rpm. What is the difference? So, difference ns minus nr slip speed, we can say that is nearly 200 rpm. This is a relative speed between our rotor conductors and rotating magnetic field. Okay, so now in this case, what is the relative speed? Here is ns is equal to, so same ns is equal 1500 rpm. Okay, now what is the speed of this one? N is equal to 0. What is the relative speed? 1500 minus 0, thus 1500 is the relative speed between the rotor conductors and our synchronous rotating magnetic field. So that's why here induced EMF in the rotor conductors is a maximum. The frequency also equivalent to the stator. Okay, the reactance value, impedance value also increases here. Whereas once the rotor rotates, then at a speed, for example, 1300 rpm, then what is the relative speed? Only 200 rpm. What is the relative speed here? 1500 rpm. Then, so once the relative speed is reduced, then EMF induced in the rotor, that is equal to ER also reduces, frequency also reduces, impedance value also reduces. Okay, the impedance value also reduces. Why? So already we have seen that. So what we have seen? So here under condition ER is equal to S into E2. What is the S? Slip. What is the percentage? 2%, 3%, 4%, maximum 10%. The slip itself in points, 0.2, 0.4 value. So automatically induced EMF is reduces. At the same time, the FR, the frequency under running condition, this is S times of F. So it is a 50 Hz. Now 50 into 0.02, 2%, then we are going to slip is the frequency of the rotor is very, very low. That's why we neglected iron losses in rotor conductors. Okay. Now at the same time XL also, what is the X2? X2R, that is equal to S into X2. Okay, that is equal to omega F. Frequency changes. Here frequency changes, automatically this also changes. This value also changes. So that means, dear students, please remember that this case is the at rotor yet to start. At rotor is blocked. That is the rotor is at standstill position. This is the rotor under running condition. For example, we take in the 1300 rpm. The slip speed is the 200 rpm. At that condition, what are the values changes we have seen? So these parameters already we have seen in previous classes. Okay. Now, so when rotor starts running, the relative speed between the rotor conductors and the rotating stator flux is decreased. The rotor induced EMF, which is directly proportional to the relative speed, is also decreased. Already we have seen. So, and may disappear altogether if rotor speed become equal to the speed of the stator flux. That means if the what is the slip? So, that is a slip speed is equal to slip speed is equal to what is the value? That is equal to ns minus n. Okay. Now, this is equal, in previous cases we taken the P is equal to 4 poles. So, what is the speed? So, ns is equal to 1500 rpm. We taken it. Now, here if the rotor also rotating near to the 1500 rpm instead of 1300 rpm, now it is rotating at 1500 rpm. What is the speed? 1500, okay, 1500 minus 1500, then we are going to get 0. The slip speed is equal 0. That is the, so disappear altogether if rotor speed is at that condition both are equal. At that time, what is the torque? Our aim is to find what is the torque, what is the current, what is the power factor. Everything we are going to calculating in this session. Okay. Hence, for a slip S, the rotor induced EMF will be S times the induced EMF at the standstill condition. So, we have covered all these things. So, we summarize that, therefore, under running condition ER is equal to, already we have seen, okay, everything we have seen. So, please remember, my dear students. So, this is by repeating this one. So, you are going to know everything. This is equal to the ER, that is the running condition induced EMF the rotor conductors is equal to slip times of EMF induced under standstill condition, and the frequency also this one. We derived the equations also. So, in previous class, so these are the points you have to remember. That means here whatever the, this is equal to stator and this is equal to rotor. So, these values are the rotor values under speed of slip speed. Okay. Now, after knowing this all things, now I am going to find the how much torque is developed in the rotor. I am going to equation. So, torque equation, torque, how the torque is developed, that depend upon what factors. Okay. So, let us see. Now, you know that this is a stator, this is a rotor. Okay. So, rotor is connected to some external mechanical device, rotor shaft. Okay. Now, here what is happened? 3-phase supply is given, that is equal to voltage, the power we given the P1 is given, that is equal to 400 volts, 50 Hz supply is given. Then the P1 is given. Similarly, what is happened here? In rotor, stator has is the stator core as well as it has the stator winding also. So, that means whatever the EMF induced, that is the E1 self induced in the stator. Okay. So, this P1, what is the P1? P1 is equal, we can write it, that is equal to, P1 is equal to input power to the 3-phase motor. What is the P1? So, we can write it, P1 is equal to root 3 VL IL cos phi. Okay. This input power is given to the electrical input power given to the our motor. Here this energy is used to utilized in this stator to produce the RMF, rotating magnetic field. During this process, the electrical energy is consumed. Some of the energy is consumed in the form of, what is the energy? That is equal, because due to the presence of winding there is a stator copper loss. At the same time, it has some laminations also, stator core also. Due to this one, it is some iron losses. Okay, iron loss. So iron losses, as we know that, what is iron losses? One is the eddy current losses, another is the hysteresis losses. That means here energy, whatever the input power P1 is given, some of the energy is utilized for heat energy in the form of copper losses and some iron losses also here, and remaining power, this is the power P1 minus these two losses. Okay, stator copper losses, stator iron losses. So we are going to get it, the output of the stator. Okay, dear students, don't confuse it. So you take the okay, so that means here you have taken the P1. So here wasted in the form of P copper loss of stator and P iron losses. Okay, so this is that means equal P1 minus P copper losses plus P iron losses is equal, we are going to get the P2 output. This is the input. Okay, these are the losses, these are the output. Okay, stator input is this one, stator losses are this one, and stator output is this one. So we represented P2. Okay, so this P2 comes here in the form of magnetic field. Then what is inside? This is a rotor. Okay, so now we can write it as this rotor. So rotor also has some rotor winding, the winding wound on a core material, some iron core material. So that means what are the P2 input, P2, this energy is utilized here, so to meet the rotor copper loss. Okay, rotor copper loss. So what rotor copper loss, and some energy utilized for iron losses, but this iron loss is very less in rotor due to the frequency itself very less. Okay, that's why we are neglecting the iron losses of rotor. Now what is happened here? So here it is generating the some PM, mechanical energy. So what this electrical energy converted to the magnetic energy, rotating magnetic field, that is converted to the mechanical energy. Now PM is the mechanical energy, that is the rotor output in the form of mechanical energy. Okay, mechanical energy. That means here the P2 input minus losses. What are the losses here taking place? So rotor copper loss is equal to the mechanical energy developed in the rotor, PM. So that is a PM. Now once the mechanical energy is given to the shaft, shafter is rotating. Once it is rotating, there is a losses takes place in the friction and windage losses takes place at the bearing. So we have to subtract that one. So that means whatever the PM, total mechanical power developed, is equal to, or we can write it similarly. So, we can write it the PM so this is equal to, you can write the power losses due to the friction and windage losses at bearings is equal to P shaft, the net power available at the shaft is ready to take the load. This is the overall output of motor, okay, whereas the P1 is the overall input to the motor, and P copper loss, you can see the P shaft power is the overall power output. Okay, so last class we have seen all these things. Okay, so dear students, after knowing this one, so we are going to do the same thing. Okay, now let us here, so let us consider one induction motor. Okay, it is a stator winding. So given the 3-phase supply, and this is equal, we can say the P1, and it has the rotor, and rotor also rotor winding. It gives the output is the PM mechanical power, and it will enters, that is equal P2 is the rotor input. Okay, so rotor input. As we know that P2 rotor input, the P2 can be written as a P2 is equal power in rotor input power or output of the stator, that is equal to rotor input is equal, we can write it angular velocity into torque. So our aim is to find the torque here only. Okay, the torque is equal, I can write it, so P2 by power by omega. What is the omega? Omega P2 is the power in watts divided by 2 phi ns by 60 is converted the RPS. Okay, then this is the value. So I am going to get it. What is the torque? The torque, I can write it, the P2 by ns into 60 by 2 phi. Okay, so this is the one equation you can see. Okay, now you know that the P2 power input to the rotor, and rotor has the rotor copper losses. Okay, so from rotor copper losses, so we are going to get the PM. We know the relations, rotor copper loss is equal to, so S times of P2. S is the slip times of P2. At the same time, PM, that is equal mechanical power developed, also 1 minus S total minus S into P2. Already we know. Okay, mechanical power developed in terms of can be calculated in terms of input to the rotor, that is 1 minus slip into P2, we are going to this one, and S into P2 we are going to the rotor copper losses. Now what are the rotor total copper losses? Can I write total copper loss of rotor? Total copper loss is equal to 3 into 3 windings, we are going to I square R2. I square R, just losses. Okay, I square R loss, that is the total copper loss. Now these are the total copper loss. So I want the P2 in terms of copper losses. Okay. So what is the relation between the P2 and copper losses? So I can write it. So what is the formula? Rotor input P2, can I write it? So here the rotor copper losses, I can write it. Rotor copper losses is equal, can I write it? S into P2. I want the P2. Okay, S will come here. Simply I can write it. The P2 is equal to 3 into I2 I square R2 by slip. So this is a P2 value. That means rotor input can be written as a 3I square R2 by S. So total copper losses by slip terms, we are going to get the total input to rotor. Okay. So if you know the P2, then so what is the rotor current? Now in this case I want the rotor current. If you know the rotor current, if you know the S slip, so I can easily calculate the what is the rotor input. Okay, just you calculate the what is the I2. Now in this case we can write it simply. What is this one? So this is a rotor input EMF induced under the condition ER, okay, is equal to here impedance of this coil. Similar. So this is a Z1, Z2, you can write the Z2, that is called, what is the value? Slip times, that is equal to R2 plus S into X2. Okay. Now what this is one? ER is equal to, you can write it S into E2. What is the current? I2. Okay. Now dear students, don't confuse. Now what is the I2? I2 can write it. Here what is the voltage by impedance? That is, what is the voltage? ER. What is the impedance? Z2. Now I can write it. So what is the ER? I can write it S into E2. Now what is the Z2? R2 plus J of S X2. So this is the EMF equation. So I can write it, this current I2, further can write it S into E2 divided by under root of R2 whole square plus Sx2 whole square under square. So this is another equation. Okay. So this is another equation. I2 value I know. At the same time you substitute this value in that one. So this I2 in terms of E2 in terms of slip, in terms of this value. So what is that one? So what is the value we are going to get it? So here P2 value I am already get it. What is the value P2? So that is equal 3I2 square R2 by R2 value by S value. Okay. Now 3 R2 by S. So this value only I am going to, this value I am going to write it. Okay. So this is a value. Now you can write it. So I am going to write it, this value I2 is equal S into E2 by root R2 whole square plus Sx2 whole square under root whole square. Okay. Simply I substituted in this equation. Okay. So just you multiply it. Now what you are going to get it? So simply multiplying, so this one by simplification, so we are going to get it. Okay, dear students, this is very easy. Okay, you can do it. That is equal to 3 R2 by S. So that is equal S square E2 square divided by R2 whole square plus Sx2 whole square. This will cos root this one. Okay, this is the equation. by simplifying this one, so here S and this S will go. Okay, that we are going to get it 3 into E2 whole square, okay, into at the same time S also there is one S 3S E2 square into R2 divided by R2 whole square plus Sx2 whole square, that is equal to P2. So we got this equation. Okay, so what is the P2? P2 is, can I write it? So T torque, I want this value now, omega into, you can write direct omega this one. So I want this value, so P2 I know this one, so I want the only torque, can I write it? So P2 by omega. So what is the P2 value? This value. What is the P2? 3 into S into E2 whole square, okay, divided by R2 whole square plus Sx2 whole square, okay, into R2. Okay, so this is divided by omega. This is the torque developed in the rotor in terms of R2, in terms of this one. What is the W? W is equal, can write angular velocity, that is equal 2 phi n by 60. 2n by 60. Okay, so this is the value. Okay, so torque we got it. So finally, so we are going to get it, the torque equation. So torque equation, I can write it. Okay, torque, can I write it? This is equal to, torque is equal to, so what is the value? So I am going to get it simply by substituting this value. So that is equal to, so 1, that is equal to 60 by 2 phi n, okay, into 3 S E2 whole square divided by R2 whole square plus Sx2 whole square into R2. So this is the equation. For simplification, we can write it. So we know the 2 phi n s by 60, that is, so we can write it. So in terms of 6 into 3, we are going to multiply. So then, so we are going to some value. So this value I can write it. So this is this value I can write it in terms of some k constant. So I can write it, T is equal to k into S E2 whole square R2 by R2 whole square plus Sx2 whole square. So this is the equation. That means where is k value is, can I write it? K value is equal to the constant value. Okay, so that is equal to, so 180 by, so that is a 2 phi ns. So where is the k is the proportional constant. Okay, so this is the torque equation in a induction motor. Okay, torque equation in induction motor. Just what we have seen here, we taken P2 in terms of copper loss. Copper loss is equal 3I square R. I means current. We calculated current is equal to voltage by impedance value. Simply substituted that value in the P2 value. Then we are going to get the torque. This is the final equation. Okay, so dear students, so I think you have the idea how to derive this equation. Okay, everyone is okay now? Or so if you are feeling it is difficult to remember, so what is it is very simple. So you can see here what is happened here. First what we have taken, simply we taken the, you can see, so you have taken first the what is the stator P1 and what is the P2, and from the P2 in terms of we take the Pm. Now P2 is equal omega t, we taken is the torque, our torque is equal P2 by omega, that is the 2 pi ns by 60. This we are used in last case. Okay, now same this is used in last case. Now this P2 value, what is the torque? T is equal this value. So what we have written, T is torque is equal to P2 by 2 phi ns into 60. This is the torque equation I required initially. So I want the P2 in terms of copper losses, in terms of current. Torque is the mechanical output. I want the P2 is the electrical. So I want the torque also in terms of electrical quantities, I value I required. So then, that purpose of P2 I written. What is the P2? The mechanic, that is the rotor input value. Rotor input value I can write it in the form of copper loss, where we know that the copper losses is equal to S slip times of P2. So I want the P2, that is the P2 is equal, I can write it. So rotor copper losses by S. Where is the rotor copper losses is equal? This total copper loss, 3 I square R2, 3 phase. And substituted this total copper losses, this here, and S is the slip, then I can go to the P2. So I can write the P2 is equal, this is the value I written. Now here I require the P2 we know. So I require the I square value. What is the current? So I written that this is equivalent to the circuit diagram of rotor, that is equal one source EMF induced in the rotor, and this is impedance, rotor conductor, the parameters, the closed one. So based on this one I calculated the what is the current. Current is equal voltage by impedance. Simply I written this equation. I written this equation. So based on this equation, so I simplified the current value I calculated here and substituted in the P2. What is the P2 this here? Here we require the P2 value now. So where is the P2? This value. I substituted here. So P2 value is substituted. Then I am going to get that. So P2 value is this much. Then so the P2 value is equal to this value now. So that means the P2 value is equal to this much. But what is the value? P2. This is the omega into torque. I want the torque. Initially we have seen. So that is called torque I required. So I can write the torque is equal P2 by omega. What is the P2? I substituted from this value. Then I am going to get it. Finally, so this is the equation. I am going to get the T is equal K into slip times of E square R2 by R square plus Sx. This is a torque under running condition of rotor. This is the derivation of torque equation in rotors. Students, you have the syllabus. This is the derivation of the torque. If you feels somewhat hard, so these are the steps. So another method I am going to explain very quickly and easily. Please concentrate it. So what is happened here? So another alternate method. Alternate method of torque. Now we take the another method. What is that method? Now we can see it. Let us assume. So we know that the torque DC machines and synchronous machine we have seen that the torque is directly proportional to the flux I2 and cos phi 2. So we know this basic formula. The torque is directly proportional to the flux, current in the rotors, and the power factor between these two. Where so we know that the voltage induced in the rotor directly proportional to the flux. If the flux is more induced EMF. So what is the formula? So already we have seen EMF induced in the transformer is equal 4.44 phi F N2 and Kw is the winding factor in case of the rotor. So transformer is the same. That means E2 is directly proportional to the phi 2 here. So here substitute this value. So I can write it here. So torque is equal to the directly proportional to, instead of phi I can write E2 I2 cos phi 2. This is the direct equation, torque equation. If you know this torque equation, So simply substitute the what is the E2 value, what is the I2 value. Okay, now write the same equivalent circuit diagram. This is the stator, this is the rotor parameters, this is the short circuit. This is Z1, this is the ER. Okay, now you know that under running condition, what is the values of this one? So I can that ER is equal to S into E2. Okay, what is the Z1? Z1 under running condition R2 plus S into X2 J constant. Okay, these are the values. Now substitute the ER, you know that what is the ER? This is the E2, this is the one under running condition, this can be the ER, you can take ER. I2, this is the I2. How we are going to find the I2? Here I want the current I2. I2 is equal to, what is the formula? I2 is equal to voltage by, similar to the voltage by current. So not impedance, okay, impedance. So that is equal to, what is the voltage in rotor induced EMF? ER. What is this one? Z2 under running condition, that is equal S into E2 by, what is this one? R2 whole square plus Sx2 whole square under root. That is the rotor impedance value at slip speed. Okay, this is the value of I2. At the same time, I require the cos phi 2. So as we know that this is equal to triangle, this is a phi angle, this is a Z, this is a R, this is a X. What is the cos phi? Cos phi is equal to R by Z. Okay, simply this value. What is the R? R2. What is the Z2? That is equal R2 whole square plus Sx2 whole square under root. Okay, you know the cos phi 2 value, you know the I2 value, simply substitute in the equation, in this equation. Okay, then so we are going to get it, what is the value? So that is called torque is directly proportional to E2, that is the ER. Then so we are going to the I2 cos phi 2. Okay, then so that is called what ER? Here you can write the E2. Okay, that is the voltage is the E2. You can take the E2. IR, what is the I? I we have got it from this equation. Substitute this value. What is the value? S into E2 by R2 whole square plus Sx2 whole square under root. Okay, now cos phi 2 R2 by Z2. Z is equal same R2 whole square plus Sx2 whole square under root. This is the torque proportional. Now here E2, okay, R2. Simply substitute the torque is directly proportional to, so you can write it S E2 whole square by the same values. So only simple R2 whole square plus Sx2 whole square into R2. So this is the torque equation. Previously we calculated torque. So we can take in the torque is equal some constant into S E2 whole square R2 by R2 whole square plus Sx2 whole square. So this is the equation already we have drawn. This is very simple. Okay. So this is the alternate method. In alternate method, what we have seen, dear students, you can see it. In alternate method, so from the basic equation, so torque equation we know that here what is the torque equation? So here a torque equation, this is the torque equation. From the torque equation, so what is the phi? I2 cos phi 2. So here this is the another. So, the EMF induced in the rotor is directly equal to the flux. Then we can write it because we know the relation between this one. From this one, so we calculated ER Z1 I2. So, find out what is the current I2. So, I2 is equal to voltage by current. So, substitute this value. So, voltage by impedance value. I substitute this value. I am going to get this is called cos phi 2. This is the I2. Both are substituted in ER2. This is the E2 and substitute I2 and cos phi 2. Then I am going to get it. Final equation. This is the torque is equal some constant into S into E2 L square by R2 by this one, where K is equal to, we know that. What is the formula? K already we know that. So, that is the K value, that is equal to 2 phi ns by 60. Okay. So, that is already we known. Okay. 2 phi ns by 6. No. So, 60 by 2 ns. No? Let me. Now, this is equal, we can write it. What is the value? That is equal, we can write it 60 by 2 phi ns into 3. So, last class we have seen that one. That is equal 180 by 2 phi ns. That is K value. Okay. So, this is the final equation we are going to get it. So, what is the torque? Torque is equal to, so is equal some constant into S slip into E2 whole square divided by R2 whole square plus S x2 whole square into R2. So, this is the final equation of rotor of induction motor. Okay. So, dear students, so these are the equation derived from basic scratch. Okay. Now, you can see the same animation this one. Okay. So, here you can see it. So, here the stator. Okay. So, this is a stator 3-phase supply connected to the 3-phase input supply. This is a rotor winding and this is a external resistance added to this rotor restart. Let us neglect these things. Now, concentrate this one. Okay. This is the P1 and it will give you the P2, it will give us the PM. We are concentrating this one only. Now, the P2 in terms of copper losses, okay, by slip. So, we are going to concentrate this one. Okay. Now, where T is directly proportional to the phi into IR into cos phi 2. Next, this is we know that. So, phi r is equal to ER, IR cos phi r, this is the equation, and where ER is the rotor EMF for phase under running condition and IR is the rotor current for phase under running condition at slip S. And now, ER is equal to S into standstill voltage. Now, IR is equal to the current induced in the rotor conductors is equal to ER by ZR. Simply I substituted values. Okay. So, I am going to get IR value. At the same time, so this is the IR value. So, as per the impedance triangle, so I am going to write it cos phi r. What is the cos phi r? This is the cos phi. Cos phi is equal to this R2 by Z value. Okay. R2 by Z. So, you know the R2 is a constant, Z is equal this value I can write it. Okay. This value only. Then I am going to the cos phi is equal to R2 by root of this one. From the equation we are going to get the torque, substitute the torque equation, original torque equation. Then we are going to get this one. Okay. So, where K is a proportional constant. Then finally, we are going to get the torque is equal to this formula. Okay. So, K1 proportional constant, some slip and E2 whole square divided by this value R2 whole square plus S x2 whole square into R2, that is equal torque of rotor under running condition at a slip of S. Okay. So this is the values already we know 3 by 2. So we have seen this all things. Now hence in that case expression for the torque becomes, so this is a formula, we substituted the omega value, the P2 we calculated, omega value we are going to get, this is the value. Okay. So here you can see, remember that this is the 3 by 25 ns by 60. So RP, we are RPM, I require the RPS by 60. Okay. So I am going to get this at standstill condition. So what is the torque? Torque is equal to K1 into S into, okay, S into E2 whole square R2 by R2 whole square plus Sx2 whole square. Okay. Now if S is equal to 1 value, then what will happen? Then so this becomes the 1, this becomes the 1. Okay. Then so what we are going to get? K1 into E2 whole square R2 by R2 whole square Sx2, simple, at standstill condition. Okay. Now so what is that equation? That equation is equal to standstill condition, the torque, okay, torque at standstill condition, that is equal torque at standstill condition is equal to, that is equal, you can write the K1 E2 whole square R2 by R2 whole square plus X2 whole square. This is a formula at standstill condition. Okay. So this is a one equation. Now I want to find that maximum torque. What is the maximum torque? It is the extreme bearable torque which motor can produce without any sudden decrease in its regular speed, but for a short time interval. When we are going to add the load, for example, already you know that this is the spring load we are adding on motor. Under normal condition, the spring is loose, the rotor is running at normal speed. Once you are adding the load by tightening the spring load, okay, so what will happen? So there is a friction will takes place more and more, then the rotor speed will decrease. If tighten the further, then the speed will decrease. If tighten further, decrease. If tighten further, decrease. At one stage it will stop. That is known as the pull out torque. Okay. So it is a extreme bearable torque which motor can produce without any sudden decrease in its regular speed. So it will produce the torque, that is the maximum torque. If that is the only short period of time, it will produce. If the load is continuous, then automatically motor will comes to standstill position. It will produce a serious damage for the rotor of the motor, and the speed of the motor will steadily slow down and motor stops its work. Sometimes there is a twisting takes place also. The load is suddenly increases, then what will happen? So it is unable to rotate the load. So that is at that time what is the torque is developed, that is the maximum torque. Okay. So let us, what are the conditions at which it is going to occur, the maximum torque is produced in the rotor. We are going to derive this one. Okay. Let us do. Under running condition, the torque of a rotor under running condition is, as we all know that is the K into phi into S into E square R2 by these values. Then this is a proportional constant in terms of this one. Okay. The condition for maximum torque may be obtained by differentiating this equation with respect to slip and equal to 0. So we are going to do the maximum torque. Okay. So what is the torque here? The torque, okay, you can take this different colors. So this is a torque, okay, a torque that is equal some constant K1 S E2 whole square R2 divided by R2 whole square plus Sx2 whole square. This is the normal equation. Now I want to do that. So this is the equation. So dt by ds, I am differentiating this equation with a slip, and after that we equate it with 0. Then I am going to get that, so maximum torque. I am going to get the maximum torque. To get the maximum or minimum, I require the differentiate this equation with respect to some variable and equal to the 0. Okay. So in this case I am going to do the same thing. Okay. So what is that one? The condition for maximum torque may be obtained by differentiating the above expression with respect to slip S and then putting equal to 0. Then what is we are going to get? So you can see here. Dear students, so maximum torque we are going to get here. So you can see here the torque at which is going this one. So there are two conditions. So the torque is slowly increasing from 0 standstill condition to the nearby speed. If increases further, this is a torque. This is you can see that is the torque. If increased further, then automatically suddenly decrease the torque. So this condition I want to know. At what condition? At what will condition it will is going to occur? Okay. So either two cases, case 1 and case 2. And you can see what is the torque. Now let us prove it. Conditions for maximum torque under running condition. Okay. So now what we are going to do? So here, so I will do on that one. We will do here. Okay. So I can see. What is the torque equation? Torque equation T, okay, is equal to K some constant, okay, K some constant, S E2 whole square R2 by, okay, R2 whole square plus Sx2 whole square. Okay. So I want to do this one, dt by ds is equal 0. I am going to differentiate this one. Then what is the going? I am going to get it. So here, so what the equation? I can see dt by ds is equal to, so just like the UV equation, S and S. Okay. So that is the equation d by dt u and v differentiation. Okay. You know that thing. So what is the first differentiate? That one. So you take the k into numerator, you differentiate. So S is equal to 1, it becomes E2 whole square R2. Okay. So you substitute this value. What is this one? R2 whole square plus Sx2 whole square. Okay. Now remove this one. Now minus, we are going to this one, is whatever the value, k into S into E2 whole square into R2. Now differentiate this value. So what is the differential value? So this becomes a 0, here is a 2, it will come 2 into S into x2 whole square. Okay, this is the value divided by, so R2 whole square plus Sx2 whole square, this is whole square. Okay, that equal to 0. So now it comes to the 0. Then I am going to get, what is the equation? So I am going to get it, k E2 whole square R2 into R2 whole square plus Sx2 whole square, okay, minus k value, S value, E2 square, okay, R2, okay, into here 2 into Sx2 whole square. Okay, now you can see is equal to we are going to get this is equal to 0. Okay, now what has happened? Minus k get cancelled, then e square get cancelled, r2 you can take the r2 taken out. Okay, now what is the remaining here? So here, so what are the value? R2 whole square plus sx2 whole square. So you take the main, that is equal. Then, so what is the value we are going to get here? So s into s, 2s square x2 whole square. Okay, na? That is the value. Now here we are going to, what is the value? So here this is equal, same thing, I can write it, this is equal to 2 into sx2 whole square. So now here r2 whole square is equal to this minus this one, we are going to get the sx2. Okay, so here I am going to get it. So not sorry, so I am going to this is called bracket now. Okay, write it bracket x2. So here under root both side we are going to r2 is equal to s into x2. So this is the condition for maximum torque. Okay, simply that means, so here dt by ds we equal to 0. So we are going to get it at slip speed maximum. So when r2 by x2 comes, that means the maximum. That means what has happened? The reactance of rotor when it becomes to equivalent to the rotor resistance value, at that condition it produces the maximum torque, that is a pull out torque. Okay, that means here what will happen? If the s depend upon the slip is dependent on the speed at which it reaches at that slip into reactance value, product of this value equal to this resistance value, at that condition it is going to produce a maximum torque. Okay, so in previous we have seen what is that one? So here the speed versus that one. Okay, that means here you can see that graph, this is a torque, this is a, we can say this is a speed, okay, n. If this is a speed, at starting the speed, rotor speed is 0, then that means it is a, initially the torque, it has a some torque, okay, the torque, it is a torque, then slowly increasing, at one stage it becomes the maximum. This is a maximum torque, T max. That means at that condition, what is the NR? What is the, at that condition, what is the slip? The slip is known as the maximum slip. That the slip at which maximum torque is occurred. What is the condition? That is equal to, we are going to get that is called R2 by X2. That means the slip value, the reactance value, the under running condition, the reactance value becomes to the resistance value. At that condition, we are going to the maximum torque. This is known as the T max. Okay, so this is the torque equation. Now let's see here also same thing. So you can see here, the we taken the another y is called 1 by z is called this one, we taken this one. So here I taken for the simplification, no problem, you can do anyway. So we are going to get it, the equation, simple equation, say dy by ds, we are taken this. So then finally we are going to get it, this is the equation. Okay, so you can see here the what is the torque HP, this value, how the maximum torque is going to occur. At that condition, what is the current of this also, it is going to decrease value. Initially current is more, when the speed increases, the rotor current also decreases. Okay, so that is the thing you have to remember. Hence the torque under running condition is a maximum at that value of the slip S, which makes a rotor reactance for phase equal to rotor resistance for phase. So, that is called, we already have seen. So, Sx2 equal to R2. So, this value. Okay. The slip is sometimes written as a SB, that is a braking slip or maximum torque, and the torque is we can take the maximum pull out torque, we can say the maximum torque. Okay. So, what is the condition? So, condition already we have seen. So, this is a condition. Okay. You can see the torque is equal simply the condition of the maximum torque under running condition. Now, we are going to substitute this value wherever the value or the SR2 is equal to Sx2 condition. So, I am going to substitute the Sx2 value in terms of R2. Then I am going to the maximum torque condition. Okay. So, this is the condition I am going to substitute in my equation. So, what will happen? So, I know the what is the torque? Torque is equal to, that is equal, you can write directly some K1, and that is equal to S into E2 square R2 by R2 whole square plus Sx2 whole square. Okay. Now, I am going to write it. So, wherever the Sx2 I can write the R2. Okay. Then what will happen? So, simply write it. Okay, you can go to this equation. So, what is the torque? Torque is equal to, I substitute the K1 some constant S E2 R2 by R2 whole square plus Sx2 whole square. This is the equation. Now, substitute the value. What is the substitute value? That is equal to R2 is equal to Sx2. Okay. Substitute in this one. Then I am going to get it K S E2 whole square R2, okay, by R2 whole square plus, here I can add the R2 whole square. Okay. Then K into S into E2 whole square R2 by 2 R2 whole square. Okay. This R2 get cancel. Then we are going to get, what is the equation? K into S into E2 whole square, okay, by, so I am going to get it 2 R2. 2 R2 I am going to get it. Okay. So, that means the condition maximum torque is equal, I am going to get that final equation. So, K into E square by 2x2. So, 2 R2 I am going to get it. Okay. So, in terms of R2, this is the one equation, this is the T max. Similarly, I can get it in terms of x2 also. So, T max, I can write it T max also in terms of here R2, I can written the R2. I can write the x2 also in terms of x2. Then I am going to get that, what is the value? K into E2 whole square by 2 into x2. So, this is the formula I am going to get it. So, this is a maximum torque equation in terms of x2. This is a maximum torque value in terms of R2. Okay. So, dear students, please remember this one. T max is equal to some proportional constant into E2 square by 2x2. Okay. So, that is the expression for maximum torque equation. Same, these are the, we derived this thing. Substitute this value. So, I am going to get the final equation. So, this is the final equation I am going to get it here. Okay. Some proportional constant, this is the, I am going to the proportional constant. From the above, it is found that the maximum torque is independent of the rotor resistance as such. So, what is the T max? T max, we in terms of x2 we are writing What is the value? We are going to get k into E2 whole square by 2x2. That means yet R2 is not there. That means the resistance of rotor independent of the maximum torque developed, independent of the maximum torque of R2. Okay. So, this is the equation. However, the speed or slip at which maximum torque occur is determined by the rotor resistance. Now, in this case, maximum torque is independent of R2, but at which the slip going to occur, so depend upon the rotor resistance, because S is equal to R2 by X2. Okay. So, similarly, so we can write it the torque becomes a maximum when rotor reactance is equal to resistance. Hence, by varying the rotor resistance, you can see here, by changing the resistance inside outside the rotor reactor starter, we are going to get the maximum torque in slip ring induction motor. Okay. So, that is the formula. So, hence by varying the rotor resistance, maximum torque can be made to occur at any desired slip. So, any at motor speed we are going to get the at which we are going to change some maximum slip torque can be adjusted by adding the some external resistance into the rotor circuit. Okay. So, dear students, so what we have seen here, and what is another conclusion? The T max is equal to some k into E2 square by 2x2 Newton meters. The maximum torque varies. Here you can see the maximum torque varies as tensile reactance. That means torque varies inversely. So, if you are seeing that one, another equation, what is the equation? Already we have seen. So, that equation you can see here. Maximum torque varies inversely as tensile reactance. So, here the equation, what is the equation? T max is equal to some constant into E2 whole square by 2x2. T max directly proportional to the E2 square, T max inversely proportional to the x2. Okay. That means if x2 and T maximum torque is inversely proportional, is directly proportional to the E square. Okay. Please remember these things. Maximum torque varies inversely as tensile reactance, hence it should be kept as possible as small to produce a maximum torque. Maximum torque varies directly as a square of the applied voltage. For obtaining the maximum torque at starting S is equal to 1, the rotor resistance must be equal to rotor reactance. Okay, at starting condition. Okay, so these are the relations between what is the torque developed in the rotor and how the rotor torque varies based on the slip, based on the standstill voltage and based on the reactance value. So, we derived in this equation. Okay. So, dear students, we will see what is the relation between the torque at normal load, torque at maximum, torque at standstill standstill condition. Okay. So, let us do these relations in the next class. Okay. Thank you for listening my class.